Hi, thanks for joining me. Today I'm going to be going over week 1, problem 1 from the Invariants Michaelmas term weekly competition. So the Invariants is the Maths Society at the University of Oxford, and each week during this term they're going to be releasing 3 different maths problems which you can try and solve and win some prizes for. There'll be 3 problems every week. You've got a week to try and solve them and submit your solutions and all that sort of stuff. I'll leave a link in the description below to the Facebook page where they'll have more details on the competition. Anyway, I'm going to be providing a solution to week 1, problem 1. Let me state the problem, and then if you want to have a go at it, you can have a go at it, and then I'll get stuck into a solution. Okay, so we have S, a subset of the natural numbers, and it has the property that when you add up the reciprocals of the elements of S, you get a finite number. So in other words, the sum of the elements n in S, the sum of 1 over n, where n is an element in S, is less than infinity. Now we want to prove that this thing holds, i.e. the limit as n goes to infinity of the cardinality of this set here, where this set is S intersect 1, 2, 3, 4, all the way up to n, divided by n equals 0. So we want to show that the limit of this number here equals 0. If you want to have a go at this problem, pause the video now and give it a go yourself, and I'm going to get stuck into a solution. Okay, so I guess a couple of things to point out before I get stuck into a solution is if there was some S which didn't work, so either there was some counterexample S, well then S would certainly have to be infinite, because if S was finite, then it has some largest element, say M, but then of course then that means that this set here, S intersect 1, 2, 3, all the way up to n, will eventually just be the set S, i.e. when little n is bigger than or equal to m, then S intersect 1, 2, 3, all the way up to n will just be the set S, and thus a constant set, and its cardinality will be at most m, because its biggest element is m, and thus this thing here will be at most m over n, but then taking n to infinity obviously makes that limit 0, so that won't be a counterexample. So if there is a counterexample set S, then S would also be infinite, and also I guess one thing to notice is that S can't be the natural numbers, because then we'd have the sum of the elements, or sum of the reciprocals of the elements in S would be the harmonic series, which we know diverges. I made 2 videos about that, and I'll leave links for those in the description below. Okay, so now what we're going to do is suppose a counterexample exists, i.e. there exists some subset of the natural numbers S for which this thing holds, i.e. the sum of the reciprocals of the elements in S converges to some finite number, which here I'm going to call L, but the limit as n goes to infinity of S intersect 1, 2, 3, all the way up to n divided by n does not equal 0. Okay, so that's our sort of contradiction. We're assuming some counterexample exists. Okay, well then that means, well obviously S is infinite by the argument I just presented, but there exists some an, a sequence in the natural numbers, a subsequence of the natural numbers, with this property here, and some epsilon bigger than 0, such that S intersect 1, 2, all the way up to an, divided by an, is greater than epsilon. Okay, well why is this the case? Well, if an epsilon like this didn't exist, and same for an, that means for any subsequence of the natural numbers, and any small positive number epsilon you give me, this thing here will, this is for all n, this thing here will eventually be less than epsilon, but then that means that this thing here, this set here, would go to 0, which obviously would be a contradiction to our counterexample. Okay, so there exists some subsequence of the natural numbers an and some small positive number epsilon, for which this thing holds here. The cardinality of the set S intersect 1, 2, all the way up to an, divided by an is bigger than epsilon, and that holds for every natural number n. Okay, so we have this sequence here. Now what we want to do is arrive at a contradiction. Okay, so we've just derived this property here, i.e. there exists some subsequence of the natural numbers an, with the property that there's also some small positive number epsilon, for which this set here, this number here, the cardinality of the intersection between S and 1, 2, 3, all the way up to an, divided by an, is bigger than epsilon for all natural numbers n. Now I've also written this thing here on the whiteboard. There exists some capital N in the natural numbers, for which, when we look at this sum here, the sum of the reciprocals of the elements in S, but only those that are bigger than or equal to n, we get something that's less than epsilon over 2, and that simply comes from this property here, the fact that the sum of the reciprocals of the elements in S converges, that means when we look at the tail of the sum, it will eventually decay to 0. And that's what this thing here is essentially saying, but in mathematical terms. Now what we're going to do is combine these two things here to arrive at some sort of contradiction. Right, let's look at this set here. And firstly, let's multiply through by the an in this inequality. And an is obviously positive because it's some natural number. So we don't have to worry about the inequality sign changing. Now, let's compare this number here with this number here. Okay, so obviously the set inside the cardinality thing is, in this case, is a subset of this thing here. But notice that this set here can only ever be as at most n plus the cardinality of this set here. The reason being, this set here may contain, and it may not contain, but it may contain at most the elements 1, 2, 3, all the way up to n minus 1. And apart from that, any element that's in this set will also be in this set here. So we can deduce that S intersect 1, 2, 3, all the way up to an is going to be at most n plus this thing here. Okay, now what we want to do is, well, let's take n from both sides. So it just makes the inequality this thing here. Now, we know that this thing here, because of this property here, this thing here is going to be bigger than epsilon an minus 1, which I will write here. Epsilon an minus n, sorry. Okay, so just bringing this property, writing it here. Okay, now dividing through by an, I get, let me write it here, this thing here, 1, 2, all the way up to an. Oh, sorry, this is supposed to be up to n. Sorry, from n. This set here, divided by an, is going to be at most epsilon minus n over an. Now what we're going to do is notice that when we take an to infinity on the right hand side, this side here goes to epsilon, because obviously this n over an term goes to 0. But then that means, well, choosing some an big enough, then this thing here is going to be strictly bigger than epsilon over 2. And now we're almost at our contradiction. We're going to show that this thing here contradicts this thing here. But let me just quickly go over what we've done in this last line here. We've derived up to this stage for all an. And then the argument I've used to put this epsilon over 2 here is if we choose some an big enough, and now remember an is some subsequence, but in particular it's infinite of the natural numbers, or infinite cardinality, so that means I can choose an an big enough so that this thing here is bigger than epsilon over 2. Yeah, so now what we're going to do is compare this thing here with this result here, and we're going to arrive at some sort of contradiction. Okay, so we've just derived this property here. If we choose some ak large enough, where k is some constant, arbitrarily large, then this set here, the cardinality of this set here, S intersects n plus 1 all the way up to ak, divided by ak is going to be bigger than epsilon over 2. Now we're going to combine these two results here to arrive at our contradiction. Let me rewrite this thing here, but in the reverse order. So we have epsilon over 2 is bigger than the sum of the elements in S, but those that are bigger than or equal to n. Oh, sorry, the reciprocals of the elements of S, those that are bigger than or equal to n. Okay, this thing here, this sum here, I claim is going to be bigger than or equal to the reciprocals of the sum of the elements in S, but those that satisfy this inequality here. Why is this true? Well, firstly, the terms that we're summing up are 1 over n, and that's always going to be non-negative, or positive in fact, but in particular non-negative. But because the set which I'm summing over here is a subset of this thing here, obviously this sum here will be less than or equal to this sum here. Now what I'm going to do is use the fact that we're capping little n at ak, and then we can conclude that this thing here is bigger than or equal to the sum of the elements in S, n between big N and ak, but this time we're going to choose the largest element in this set here to make the reciprocal as small as possible. So this thing here is obviously going to be bigger than or equal to, less than or equal to this thing here. But now the thing that we're summing is a constant with respect to n. So this thing here is precisely, if I can write it down here, 1 over ak times the cardinality of this set here. In other words, the number of elements which I'm summing over, which in this case is, well, an element. If it must be an element in S, but it's also got to be between n and ak. Okay, but this thing here, notice, is precisely this thing here, and this thing here is bigger than epsilon over 2. And that's where our contradiction comes into play. We've shown that epsilon over 2 is bigger than something, which is bigger than or equal to something else, bigger than or equal to something else, blah, 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 which is bigger than epsilon over 2. So in other words, epsilon over 2 is bigger than epsilon over 2. Strictly bigger than. And of course, this makes no sense. This is absurd, and thus we arrive at a contradiction. Okay, I think it's quite a nice proof. It uses sort of analysis-esque techniques, epsilons and capital N's and things like that. But it's quite a neat argument, something which I wouldn't say is too trivial to prove. It's not a straightforward proof. But yeah, I hope you have enjoyed this video. If you are new here, please do consider subscribing. I have lots of fun, different maths videos, problem solving, going through proofs and theorems and things like that. I'm sure you'll enjoy them. But yeah, that's all for now, and I will catch you in the next one. Have a great day.